Okay, let's start. So, any questions? Nothing? No one? Okay. So, I want to start by recapping the wireless technology stuff that we started doing last time. So, kind of the major points. So, I had sort of gone over roughly kind of I guess stages of radio, and just to kind of remind you, uh, we had basically there is this sort of flow of information which kind of goes on from the software handing packet to the radio stack for transmission. And very loosely speaking, you can think of it as kind of divided into um, this topmost layer, which is the so-called MAC layer, which is responsible for arbitrating access to the wireless channel. So that's the medium access control part. And then, depending upon whether it's your turn to transmit or receive, in case of the transmit path, we go through this process. Much of it is digital, where you code this information so that it's resilient to error. So this part really has to do with error. And then you modulate, which means somehow encode that information into a carrier wave, a radio waveform, and then finally convert to analog, push it up to higher frequencies, and send it out. Reverse direction, at some point, again, thanks to that arbitration protocol, it's your turn to receive and someone else's turn to transmit. So some radio signal coming in and kind of goes through the reverse pathway, where you first bring it down to a more manageable frequency, digitize it, and then demodulate, which means extract the information from the waveform. So, like for example, if the information is on the amplitude, you are going to have some processing done to extract that, and then decode, which is the reverse of which is kind of extracting bits from potentially corrupted bits, form them into a packet, and then hand it over. So from a software perspective, radios basically look like a queue of packets, and you hand over a packet that kind of takes care of it. If the queue is empty, it's going to inform you, much like the FIFO in a UART might look like, except that instead of characters, you're working with packets. There are some radios which kind of deal with things at byte by byte, some really simple radios, but generally speaking, that's not the abstraction that you see, and the kind of this packet level things are what we are seeing. The other thing that I touched upon was that how there are a few um, different ways of organizing radios, organizing wireless networks. So the one which we encounter the most, some sort of an access point. So like UCLA's Wi-Fi access points, and our devices just connect to them, potentially going through some sort of a pairing process. And then these access points talk to each other using Ethernet or some other local area networking technology. In some cases, you encounter the situation where to extend the range, you may have two access points talk to each other through some sort of a fixed wireless thing. So nowadays, it's kind of fairly common to find products which are all sort of capable of doing it. The other extreme end of topology is one where there is no infrastructure and devices just form a mesh network. They so to send information from one device to another. Any other device can act as a forwarder. So it's kind of playing the role of an access point. So each device here is both an access point or a router, as well as a source or sink of information. So this is something which is very popularly um, just a sec. This is something which is very popularly used in settings where infrastructure may not be present, post disaster, military operations, those kind of things. Um, uh, there are some nice properties out here. Foremost, since there is no infrastructure, so these networks are designed so that once you sort of power them up or a new node comes in, it kind of figures out how to talk to the others. So there is a high degree of sort of self-healing, self-configuration, those kind of things happen. But it's a much more sort of challenging thing because you can't rely on any infrastructure. But you do encounter this a lot in network embedded systems, particularly, for example, home automation. People may buy something, a wireless switch, something, put them at random places. You may not have coverage, and again, these things kind of figure out how to reach back to to your home network. So these smart lights that you find, or so they typically come with one access point which you place somewhere in the home, and then the light bulbs can talk to each other and multi-hop their way. So that leads to kind of most common way that you will encounter these things typically, which is you do have an infrastructure, but you also have the mesh, and which basically means that some of my devices in the mesh network are also connected back to the wireless backbone, and other devices may multi-hop to that. So there are we'll talk about some commercial standards which kind of follow this thing, but the most common one which gets used is Zigbee. Bluetooth is not like that, or at least not until very recently. So Bluetooth always, for the most part, has been in this model of things, except that the access point was your phone. Um, Bluetooth 5, which has just begun to roll out, does have mesh networking kind of capability, so it is capable of doing this. So you may have um, some some device which is not immediately talking to your phone or Raspberry Pi, but is multiple hops away. Actually, Bluetooth has had this mode for a while, but it was pretty poorly designed, so never really worked. It was called ScatterNet. So it's been in existence for several generations of Bluetooth, but never used. Bluetooth 5, their hope is that it will finally sort of catch on. Okay, so the other critical piece in that whole thing is this MAC protocol, how the arbitration happens, medium access control. And the foremost thing is that you want to avoid collision. In particular, the role of this protocol is to avoid collision at the receiver. So you don't want two different transmissions to be arriving at the receiver overlapping in time. Now, even that, with fancy radio processing, there are techniques by which, even though packets may be colliding, you can kind of still separate them out. Um, but uh, but that's the primary goal. There are additional goals that you would want to achieve, having to do with not starving out any of the transmitter, giving them fair opportunity to transmit, things like that. And I'd finally kind of had shown the example of how Wi-Fi ends up doing it, and the way this protocol works is, and this is very common, it's very similar to what Ethernet and a whole bunch of other systems use, that before you transmit, you have to somehow see whether the channel is occupied or not. Now, in wired networks, anyone knows how, like in wired networks, things like Ethernet, how arbitration is done, how this kind of, if you've done any networking class. Nope. Right. So how does it do collision detection? No. We are describing Aloha. Okay. So what Ethernet? So firstly, uh, so the scheme Nithya is describing is something which was among the very first scheme, which is basically you go ahead and transmit, and if you detect collision happened, then you are going to retransmit, and you'll detect collision happened because you did not get an acknowledgement back. So you just go ahead, transmit. But so that turns out to be pretty inefficient. That's a protocol called Aloha, one of the very first one of this nature. Um, what Ethernet does is the following: before transmitting, um, it checks if the channel is free or not. And if it is free, it's going to go ahead and transmit, but it simultaneously listens and it sees whether it can hear back the same thing that it is transmitting. And if it doesn't, it realizes there is a collision, and so it's the collision sense part, and then it kind of backs up. It will stop transmitting and kind of go do it later. Now, unfortunately, that strategy doesn't work with wireless, and the reason is that in case of wires, the transmit signal and the receive signal are of comparable power. So you could listen what you were transmitting also, so you can listen kind of both. The problem in wireless is that your own transmission is right next to you, whereas the other party's transmission is really far away, and so the signal you're receiving is very weak, and so collisions are hard to detect because essentially you'll always hear your signal and not kind of the other party. So that is why wireless schemes go for this kind of an etiquette where you wait for a bit. In this case, we wait for this interval called DIFS, and if the channel remains free during that period, then you go ahead and transmit. And every node does the same thing, which is whenever it feels like it wants to transmit, it will do this waiting business. Now, if channel remains free, you'll kind of go ahead. Now, there is a slight chance that there are two nodes which exactly at the same time decided to transmit, and their DIFSs are also totally synchronized, in which case the packets will collide, and then later on recovery will happen. But what happens now is there are kind of two possibilities. One is that you may have an acknowledgement, and the other is you may not have an acknowledgement, and the system can operate in both modes. If there is no acknowledgement, then the fact that packet didn't make it through would have to be discovered later by some higher layer protocol application, for example. So in that case, what happens is, let's say there was some other node in the top part, if some other node were to wake up and decide to transmit in the midst of data, then it will see that the channel is occupied, and therefore it will wait. And let's say a node woke up somewhere here while this other node had already started waiting, then it will see the transmission happen before DIFS has expired, and it will see the channel is busy, and so then it will go ahead and wait for the channel to be busy, channel to become free. So it will defer the access. It will defer the access until the ongoing transmission ends, and the channel has remained free for that DIFS interval, and then, and this is a very important part of the strategy, it will basically toss a coin and then decide how long to wait, some additional wait in a time window. And the purpose of this is that if multiple nodes woke up during this period and are waiting, you don't want them all to begin to transmit at the end of DIFS, so kind of just spread them out. So in congested settings, that kind of helps avoid kind of synchronized collision from happening. Then to additionally provide kind of a rapid feedback about whether the packet has made it through or not, there is a provision for an ACK. Now you somehow need to give ACK a higher priority so that it can be transmitted immediately. And these different IFS, interframe spacing, play the role of priority in this system. So ACK, if the receiver has to send an ACK, it will have to send it within after a gap of no more than this SIFS, which is shorter than DIFS. So the idea is that if someone was waiting, it will see the ACK also because SIFS is shorter than DIFS. So this requires that the receiver have some time, should honor this time constraint and all, kind of goes back to why deadlines and all tend to be important. So at this level, as you can see, that there is a certain response that is required. In particular, on the receiver, it has to generate the ACK packet within the SIFS period. And after the ACK is over, then anyone who was waiting will hopefully see the channel free for DIFS, and then again do that same stochastic, additional stochastic weight before transmitting the data. So firstly, SIFS in this case translates into essentially higher priority, right? By manipulating that. So in fact, 8.11 extensively uses this concept for other purposes also. There are some other similar things where you can give a higher priority to certain kind of traffic. Um, One other thing to keep in mind is that there are lots of these intervals which are basically wasted time on the channel. So all this DIFS, SIFS, these kind of things are wasted time, and to keep the impact minimal, ideally you would like them to be a small, but the challenge there is that we want these intervals to be large enough so that everyone gets to know what the state of the channel is over the network. So whatever they have to be at least as long as whatever the delay across your network could be. So these things become challenging if you are trying to attempt these things over very long links like miles or tens of miles, but over short things, they don't seem to be an issue. The other thing is all these packets, if they are very short, then the overhead of the DIFS, SIFS is going to be pretty much proportionately larger. So the sweet spot for this thing is that we should have reasonably long packet lengths for it to work. Not so the system is not going to be terribly efficient if each packet I'm sending out is a byte of small number of bytes. You will lose a lot of dead time on the channel. Okay. There are many other modes. It's a very complicated protocol. One other thing that it.
So I'm not sure exactly how it is. Does the receiver, after getting the packet, wait for SIFS and then send the ACK? Or does it send the ACK within SIFS?
It has to send it within SIFS.
Okay. So now if the channel is occupied by the ACK and the other transmitter sends the ACK, they still back off for DIFS period?
Yeah, so anything else, it will observe the act, and now it will wait until for the act to end, and then DIFS more time. So basic strategy always is, other than the receiver, if we are operating in a mode that act has to be sent, the receiver has to send within SIFS, and everyone else can only transmit after the channel has been free for at least DIFS. Okay? That's kind of the basic rule. Again, ignoring some other more weirdo modes that exist in this protocol. Another thing which comes up is the following, that so remember, even now there is a slight chance that packets may collide because two things may wake up at the same time or roughly close enough that they don't know about um, each other's existence. Um, so, and then they start sending a large packet, and those large packets will collide, and we'll get to know about it much later. So that's one challenge. There's another challenge which occurs in radios, and which is the following. Let's say someone on that side wants to send me a packet, and there is also some other node on my back who's also sending me a packet, and they're distant enough that they can transmit to me, but the two themselves are far apart that they cannot listen to each other. So situation we have the following: A wants to send to me, B wants to send to me, and let's say I'm just at the fringes of the radio range. Now what will happen is A will sense the channel, and it will find the channel to be free because it cannot hear me, right? So it will go ahead and transmit, but I will see a collision. So so in radio, the spatial distribution kind of also matters quite a bit, and one has to somehow kind of cope with that also. So one of the methods which is used is that before sending the main packet, you kind of do a channel reservation, and you do that by sending a pair of small packets. It's kind of like, I want to say, I want to send you a packet, and you would send me a clear to send. This is some kind of a handshake we do before. And only when the handshake has succeeded do we proceed with transmitting the longer packet. So this RTS CTS is something that is actually also used um, in UARTs and all also. So you can enable that mode because kind of a similar reason if I'm sending a lot of data to a destination and if the destination is not in a shape to accept it, then it will kind of decline. So RTS, one party sends it, CTS, the receiver sends back, request to send, clear to send. So in our example of A, M, B, let's say B was already sending a packet to M, or let's say the two woke up, B has reserved the channel, then if A attempts to do something, it will not get back the CTS and will not proceed. So there are all these additional stuff sort of which are built into it, but the main concept I wanted to get across here is this, that you need some protocol to arbitrate access and kind of timing and kind of this spatial distribution kind of all matters quite a bit. This an additional um, thing which happens in the following, that every time you end up into a collision situation, that is, you find that the packet didn't make it through, then the next time around, you actually are going to make this contention window even longer. That is, the idea is that if this contention window is of certain size, then you may still be able to create lots of collisions if the network was very congested. Lots of nodes were there, hundreds of nodes, whatever. So you want this thing to be large enough so that the probability of two nodes who are waiting, colliding is low. And yet you don't want this thing to be too large all the time because then you'll be wasting channel time. So the way the strategy works is that you start with a small, but then if you fail to grab the channel once, because, so let's say A and B, two nodes were both waiting, they're both going to wake up after they both see the DIFS, and then they start, and then they are waiting, they're going to select transfer time within this. One of them will win, the other loses. The one who loses is going to, next time around, is going to create a choose over a longer window. So you try to create this back off strategy so that you lower the expected load on the system. So that is this part, which is you are going to choose. So this is the contention window. This is a random number we are selecting within that, and then we also select how much we have kind of already weighted. We kind of back off accordingly. So every time you have a new frame to transmit, you're going to start with a small value of condition window and are going to keep increasing. So it's a very carefully designed thing, much more complicated than simply let's go ahead and transmit and recover, because you want to gain all sort of efficiencies out of this. I'm not going to go deeper into this because Wi-Fi is not of much interest to us specifically. CS 215, 218, some of these courses kind of go quite a bit into that. One thing that I would say is that the choice of MAC protocol is very crucial to how efficient your communication ends up being, because it's at the heart of arbitrating access to the channel. And if you ignore that, the fact that there is a MAC protocol, if you let's say you're doing some sort of analysis and you want to simply assume that the packet will always go through whenever you want, then you may end up with very optimistic numbers that may not be true. So for example, let's take something which in systems like these is often encountered. So let's say you want to send some information to a whole bunch of devices out there. Okay, maybe some sort of a time synchronization message or some sort of update command or something like that. So you want to broadcast, you want to make that information go to every node. Now on Ethernet, the task is relatively simple. There is a broadcast packet you can send out over the wire and everyone listens to it and grabs it. In a setting where you have multi-hop. And by the way, it's also easy in a Wi-Fi setting where you have a single hop. But if I have a multi-hop type setting, then what's going to happen? One node is going to send all its neighbors are going to hear. Then those neighbors have to retransmit so that things which are two hop away are also able to get that message, and so on and so forth. So now there are many different ways you can kind of approach this thing, but the basic problem you face is the following. So let's say I have a node A, and in its vicinity are two nodes B and C, and then let's say there is a node which is farther away. So A transmits a packet, it's heard by both, right? So one thing about wireless is that deep down, when you transmit something, then everyone in your neighborhood can hear it. There is no way I can prevent one device from listening to it, right? I mean, if I transmit, then everyone in my range is going to hear that, unless their radio is off. So in this case, A sends a packet, both B and C get it. But B and C know that they also are serving as relays. So B is going to have to retransmit the packet, and C will also have to retransmit the packet. So if we have bad luck, B and C transmit simultaneously, and they will collide, right? So somehow we need to stagger things out. So if you were to do dumb flooding, sort of say, which is I just send things out, and the strategy is every time I get a packet, I'm going to retransmit, then there are going to be a lot of collisions. And then, so in this case, what will happen? First time around, B and C will both transmit, the packet will collide, then our 802.11 mechanism will kick in, one of them will back off, things will go through. But all of that would have costed us time and energy. So, uh, in things like these, sort of, there would be a pretty high energy consumption. Unfortunately, when you attempt to do even sort of better things, so like for example, you might say, I'm going to construct a tree-like structure, and I'm going to be intelligent about it. Only when a node receives a packet, it's going to somehow forward packets only if it lies on the tree and not otherwise. But if your MAC is poorly designed and 802.11 MAC is not something meant for multi-hop setting, you basically don't see much of a difference between a smart routing strategy and a super dumb flooding strategy. On the other hand, there are MAC protocols which are carefully designed to minimize these kind of issues. Again, kind of off topic for this course, but there you begin to see that how you distribute the data works very closely with what your underlying MAC protocol is. So one of the best things you could do conceivably is that to minimize the chances of collision is to prevent collision from happening. So if I need to send packet to someone and some other party needs to send the packet to the same person, perhaps prior agreement we decide upon a time slot. So we agree on a priori schedule. We divide time into slots and we assign slots to entities. We can say transmitter 1 gets this slot, transmitter 2 gets another slot, and we kind of repeat this process. So we define some sort of repeating time slotted structure and give different transmitters a chance to transmit out there. So that would be an example of a MAC which seeks to minimize collision. So there are variety of these things that exist. Now, what Bluetooth uses is kind of rather interesting. One of the twists Bluetooth brings out. So this in this whole model we were talking about as if time was the only dimension and everyone was transmitting at the same frequency all the time. One thing that Bluetooth also does on top is it hops the frequency. So if two parties are talking, then they don't stay at the same frequency. They after a short bit, both parties will switch to another frequency, and after a short bit, they'll switch to another frequency. And the pattern of frequency they switch to is pre-agreed. Now, the advantage that brings is the following. Let's say there are two parties talking, A, B, and in the same vicinity there are C and D talking. If we were to be operating with a kind of MAC I described for 802.11, then they're all sharing the same wireless channel, same frequency. And so they will all sort of collide with each other. In Bluetooth model, what's happening is that the frequency at which this guy is operating, let's call it F1, and the frequency at which this guy is operating, F2, they are hopping. So across a set of frequencies, F1 is going to hop, and across a, let's say, same set or a different set, F2 is going to hop. And they'll collide once in a while, but not collide all the time. So we separate them out in frequency in that case. So in case of Bluetooth, we get this frequency hopping phenomenon to help separate things out. So even though these radios may exist close by, and even though they're transmitting at the same time, but one of the mechanisms Bluetooth brings, there is this frequency hopping capability. Frequency hopping is a form of what is called as spread spectrum. And the reason it's called spread spectrum is because we are spreading our transmission out over a large swath of frequencies. I'm spreading it out in an attempt to now reduce collision. There are other ways of doing spread spectrum also. This particular way of doing spread spectrum with frequency hopping was invented by a Hollywood actress. So that's an interesting story behind it. Heidi Lamar in apparently late 1930s. She held the patent and whatnot. So spread spectrum using frequency hopping is one approach. There is another approach to doing spread spectrum, which relies on something called direct sequence spreading, but it essentially kind of makes each bit is transmitted as a unique pattern, and those patterns are designed so that my bit and your bit will not collide. Okay, I'm kind of hand waving my way through, but 802.11 Bluetooth, one of the distinction is Bluetooth uses this frequency hopping type of spread spectrum. 802.11 uses this other form of spread spectrum. On top of it, then they have some sort of a time arbitration going on. So that's the math layer. The final layer, the next layer up, which one has to deal with in radios is routing, which is how do I get the message from one node to another node when they are not immediate neighbors. So in case of internet, if you look at like in your operating system, there's kind of a whole network protocol stack where physical layer is the Ethernet, data link is where the MAC protocol resides, network layer is where your IP addresses and routing happens, and transport layer is what TCP is. So if in terms of your jargon, so this is where MAC and all that coding and all happens. Sorry, not this. This is where MAC happens. This is where modulation happens. This is where routing happens. And this is where I'm sure you have heard of TCP, things like that. So this is where you deal with issues of congestion and controlling the rate at which you are transmitting and reliability. But what routing deals with is the fact that I have a large network where nodes have addresses. I want to send a packet to a node with a certain address. And the world would be very uninteresting if the only people I could talk to is right next to me, one hop. So on the internet, there is kind of the whole whole infrastructure where I can send a message to an arbitrary IP address, and then the routes are figured out, and the packet kind of makes its way through. So that's in the traditional network. The problem and by the way, this also therefore applies to kind of Wi-Fi type settings and all kind of same thing. The physical layer could be Ethernet or Wi-Fi. But when we are in this kind of connectivity where we have multi-hop, then things become a lot more difficult. The reason they become a lot more difficult is that right now in an internet type setting, when my machine needs to send a packet to a particular IP address, it knows very well how to go around doing it. So somewhere in my machine or in the software of my machine, there is a routing table. That routing table tells the machine to reach a particular address, which is the machine on the next hop to send it to. Now, what helps here is that the addresses in internet are hierarchically organized. So if you look at your IP address, like let's say 128.97.92.20, let's say, then all the addresses which share a prefix are going to be under a common router. So if you look at the routing table of your machine, it would have something like to reach these addresses. So my machine would know, like, if it's particular IP addresses, my example 128.97.92.20, then it would know that the local addresses which share the same prefix, it knows how to reach them because they are immediate neighbor. And those which are not immediate neighbor, it will know the address of a gateway to which it should go and send packets out. And all this routing table information is maintained very carefully all over the internet. But in our setting, now imagine these are devices, light bulbs or whatnot. We just power them up and somehow they have to kind of discover these routes. So we have to figure out how to create that routing infrastructure. There's no one, there is nothing a priori known. A particular node won't know how to go around reaching another one unless we discover that. So in these kind of systems where you have these mesh topologies, part of the job that the routing has to do is it has to figure out the topology of the network. And the way it figures out is by sending probe packets, learning. Each party learns who my neighbor is, and they somehow fuse that information so that so that we can do this thing intelligently. Now, there's a dumb way of sending messages out here. So let's say node A out here wants to send a message to some node B, and it doesn't know what the network topology is. Can you suggest some simple way of getting a packet from A to B? Like, what would be your first cut way of flooding, right? If I can make sure that my message gets to B by essentially following a strategy that I'm going to send the message to everyone, right? And so flooding is kind of the naive, simple, but extremely inefficient strategy, right? So you probably don't want to do it. But then you can think of other strategies, right? I mean, let's say I want to send a message to a node whose location I know, geographical location. So maybe what I'll do is I'll send node packets to those nodes which are closer, which are in that direction. So I can do a kind of a geographical routing. Now that's not always the wisest thing to do because I may reach dead ends. But then if I reach a dead end, it's kind of like following a maze, right? If I reach a dead end, then I can go around. So I could do that. I could have other kind of heuristics like that. Or alternatively, I could discover a priori what the topology of the network is. And then each node would somehow maintain information about who all it can reach. And then when it comes time for A to send the packet, A will say, to reach B, I better send it to this guy C, and so on and so forth. So we kind of create this infrastructure. But now imagine in all of this thing, if these nodes are dying because the battery runs out, or if they are coming in and out of the network because we have mobile nodes, the problem becomes suddenly hard because if my network is changing more rapidly, then my ability to keep the routes consistent, then I would have huge challenges out here. So this is an incredibly hard problem to kind of create this routing infrastructure. In fact, Professor Mario Gerla and Len Kleinrock and some of the folks in CSD, they are pretty well known for work in the space. Obviously, military kind of settings is one, but a lot of civilian applications, and increasingly because of IoT devices at home, we encounter these kind of settings. Now, the advantage at home is that devices don't tend to, the network doesn't tend to change very rapidly. So you still have to discover, but it's kind of more stable. But when something does die, then it can take tens of seconds for some of these systems to discover and figure out an alternative route to it. So that kind of remains a challenge from a routing. So all these bits and pieces. Okay, so final layer above this is TCP, UDP. These are the so-called transport layer. Anyone knows what transport layer's job is in a network? Anyone done a networking course? Just curious. No one. Ah, yeah. Okay. Mhm. Yeah. What do they do? What's their purpose? No, no, no. Their protocol just like MAC protocol, but their purpose is different. Yeah.
Their purpose is to take the data that's coming in on all lower level protocols and bring it up to the application layer so that it can use it in some whatever useful way.
Yeah, but what's the useful property? Okay, so yeah, go ahead.
It's reliable. Right?
Reliable, okay, and congestion control, okay, because network is busy. So one of the things that TCP does is it paces the transmission out so that you are not bombarding the network with too much traffic. So that's one goal. Another goal is it provides reliability. The network layer, the routing layer, still leaves the possibility that packets may arrive out of order or may not arrive at all, or may arrive, right? I mean, sort of delay and all. TCP makes sure that if I'm listening to packets on one side, I'll see the packets in the same order as they were being injected on the other side. So that's what TCP does. There are multiple transport protocols with different properties. UDP is another one. UDP makes no promises. So it's best effort. It's, you may get the packet, not get the packet, you may get them out of order. The application is responsible. TCP obviously is heavyweight, more complex, but gives you that abstraction. So if your application needs the reliability, use TCP, but UDP is obviously a lot more efficient. Okay, so all these kind of ideas and all have kind of now come together into sort of variety of network, wireless networks which exist in the embedded space. And I have listed some of them and I've kind of classified them into three broad categories. Those which are meant for wide area networks, um, embedded system, kind of in remote areas and all. Mid range, by that I mean, let's say a few hundred meters, and then short range, kind of room or even on body type networks and all. So wide area, we all know LTE, and there are companies which provide so-called M2M networks on top of LTE, machine to machine. Now they just use standard LTE technologies, but one of the things they do is they offer different kind of pricing models. So what I mean by that is, as a consumer, when we want to put a device on the LTE network, on the cellular network, you have to get it provisioned. You get a SIM, and you pay for some charges just for that, which is why, like if you have your car on the LTE network or your watch on the LTE network, or you kind of end up paying that way. That model is not sustainable if I'm going to run a network of embedded systems with hundreds or thousands of sensor nodes and all, and then they're using LTE. So what M2M vendors do is they basically buy cellular capacity in bulk from carriers like AT&T and Verizon, and then they basically offer models which are more based upon the data usage and all, and they keep the per device cost very simple. So if you're a farmer who wants to deploy things in a field, stuff like that, these alternative models become there. So it's more of a economic game, but the underlying technology is just LTE. Satellites obviously is another one, historically used quite a bit by scientists and all for remote monitoring, ocean, forests, those kind of things and all. Um, but the new kid on the block lately is something called LoRa, long range, that's what it stands for. And its target is city scale networks, which are extremely, so this is meant for city scale, and which are designed to be extremely power efficient. It actually uses essentially a form of Wi-Fi. Okay. But in any case, so LoRa has emerged, and a lot of sort of websites like SparkFun and all, you see kind of entire product lines because the LoRa radios are pretty power efficient, so you can buy them mated with a MCU for extremely low power implementations. LTE is also being pushed into a low power regime, and there is something called LTE Direct, which has emerged. Not very popular yet, but Qualcomm is uh, pushing it aggressively. And the idea behind LTE Direct is two LTE devices can talk to each other without needing a cellular base station. So that's why it's called Direct. Okay, so that's the wide area. Mid range, pretty much the king is 802.11 Wi-Fi. Works pretty well. The problem is it's extremely, or let's say, relatively power inefficient. And one of the reasons it's relatively power inefficient, and we're going to talk about it later, is that the underlying radio technology, there are two issues on there. So one is the underlying radio technology was the choice of modulation scheme and all were such that uh, that the amplifiers. Remember my radio picture where there was a transmitter, there was an RF amplifier, and then was a receiver. That amplifier is not very efficient. So those of you who are EEs, if your amplifier needs to be linear, then that comes at a cost of relatively low efficiency, which basically means that I need to put the amount of energy I put in, the power I put in, and the power that goes out, that ratio of output to input is pretty low. And amplifier needs to be linear if information is carried on the radio wave in a manner where non-linearity will corrupt it. So for example, let's say I was doing amplitude modulation. So then I'm carrying information on the amplitude of the signal. If my amplifier is nonlinear, the amplitude is going to be corrupted in a weird manner, and so the receiver will not be able to recover it. So certain ways of modulating information might require linearity from the amplifier, which comes at the cost of power. On the other hand, if you were to embed information in a manner that amplifier can be nonlinear, then or is not required to be linear, then you are in a more efficient regime. So Wi-Fi suffered from that in part. The other thing is, and something that we'll see, that in case of wired systems, there's a assumption that happens, which is that listening is cheap. Transmitting is expensive because I have to use that, pump out that energy, but listening is cheap. It turns out that in radios, that's not necessarily the case. So the issues out here is linearity of RF amp, high cost of listening. And the reason the high cost of listening happens is, remember when I talked about the MAC protocol? Much of the time, the radio was just listening for the channel. So it turns out that if you are just listening and not actively receiving, is not a whole lot different than actively receiving something. So that sort of creates a problem. And a third problem which comes in these radios is startup time. This is something we saw on processors also when I talked about processors being put to sleep and being woken up. For that process to be efficient, it's very important that we be able to wake up the processor very rapidly. Same thing with radios. If we are going to put the radio to sleep, then we should be able to wake them up very rapidly. And again, Wi-Fi kind of suffers from that. So while historically there have been efforts at creating low power Wi-Fi, and there are some products out there, they always come with sufficient gotchas and all that for at least a low power regime, not a very viable sort of technology, but that's what exists right now. What you begin to see in products is instead of using something like this, they might use a mesh network with a shorter range technology. And this is where we have a bunch of options out there, some of which are standards, some of which were de facto standards, became very popular, and are now being kind of kicked out as the standard ones become good enough. So one is the so-called IEEE 802.15.4. It's kind of a mouthful, but it's basically a technology designed for mesh networks, and I'm going to dive into it a little bit more. And on top of it, a whole bunch of standards have been defined, something called ZigBee, which is kind of the more popular name you might hear, and then another mouthful called IPv6 Low PAN, which stands for IP version 6, Low Power Wireless Personal Area Network. Okay, and this is a specific internet standard designed for a space where you have large number of devices. It uses IPv6, which has long addresses, so that's paying sort of catering to the fact that I can have lots of devices. Low power personal area network, as the name implies, is kind of meant for this short range kind of usage. Wireless HART is an industrial standard. I think RT stands for real time. I don't know what HS stands for. So these are all kind of things built on top of 802.15.4. So 802.15.4 defines the fee and the MAC. And then these guys define routing and transport and other goodies around it. So the place where if you have any of those smart light bulbs and all at home, they're using this. If you have a smart meter at home, which is talking to any sort of appliance, is using this. Z-Wave is found a lot in home automation products, and it too is a mesh network. So this is mesh, this is also mesh, and it's a proprietary radio standard which, while 15.4 was still kind of establishing itself, it found a niche and it's in a lot of products. So if you go for home automation products currently in Amazon or Home Depot or whatnot, most of these switches and all that you will find, they're all Z-Wave switches, or most. That's basically the current thing. And this is a mesh network. So the idea is you can buy a new thing, plug it in, and then soon after the network will figure out the new topology and learn to work with that. But it's a non-standard. It's not a standard. Basically, what it means is that you can buy the hardware and all, and there's a well-defined protocol for talking with it using the serial port, but you cannot create a competing design. You have to use that particular company's chip. No one else makes those chips until another patent will expire. So this is in the mesh domain. Bluetooth catered to the other direction, which is I have a device and it needs to talk to nearby things, sensors, talking to a phone, those kind of applications. So we all use Bluetooth in day-to-day life, so I don't need to go much into it from that perspective, but it's meant for short range, a few meter kind of thing, lower data rates than Wi-Fi. So you find them obviously in headsets and pairing your phone to the car and stuff like that and all. Now what Bluetooth missed out early on was kind of this ultra low power regime where you want sensors with coin cells which need to last for months and years and all. And that is where another proprietary standard called ANT emerged, and it got built into fitness sensors like those chest bells or stuff like that, which talk to your treadmill or elliptic machine and all, and penetrated quite heavily. And this was designed for, like I said, sort of heart rate sensing, those kind of very low data rate kind of systems. And Bluetooth suffered from both much higher power consumption and also very high pairing time. So after a previously paired device would come into range, it might take seconds for them to learn about each other. So this whole thing, kind of the early versions, the so-called classic Bluetooth, never really penetrated into this market. Then emerged Bluetooth Low Energy, which introduced on Tuesday, which basically expanded Bluetooth into ANT space. So that's kind of one way of looking at what sort of currently exists out there. LoRa is emerging, but lot of traction behind it. ZigBee has penetrated itself in smart lighting, smart metering, those kind of spaces. So let's say smart light, meter, appliance. LoRa is for city scale stuff, so you find them in metropolitan sensing and all. Z-Wave is into switches, sensors, etc. for home automation. Bluetooth we see. So kind of a very uh, uh, fragmented space, and they all kind of try to move into each other's territory. So Bluetooth pretty much at this stage has killed Ant. Although interestingly, the chips that are built in most phones, they're from Broadcom, and they actually have both ANT and BTLE. So some phones still provide support for ANT. Sony phones, for example, until fairly recently at least. So, then there are, you could see that there are industrial sort of things like wireless HART is something you'll only find in factories and all. So there's a sort of a rich space of these wireless standards which kind of exist. Okay, I am going to skip some of this stuff and go on to 15.4 as an example of what exists in this space. Now, interestingly, Hexaware has 15.4 in it. Unfortunately, Mbed doesn't expose it, so you can't use it. But the hardware is capable of doing it for the software to exist. So this 15.4, as I mentioned, is defines the physical layer and the map layer, and then on top of it, various standards have been built. Zigbee is kind of by far the most common one. This 15.4 works in two different parts of the spectrum. One is this 900 megahertz band, and the other is the 2.4 gigahertz band. Most of the devices that you will find out there work in these two bands. These one or both of these two bands. Anyone knows why? What's special about these bands? Free in what sense? That's your answer too.
Not proprietary. It's industrial.
It's called the ISM band, Industrial Scientific Medicinal Band. But what exactly does it? Okay, so the main thing is the following. Traditionally, spectrum usage was such that the user of the spectrum, as in if I am operating the radio or transmitting in it, I would need to get the license, not the manufacturer. I would need to get the license. ISM band basically said end user doesn't need to get it. The manufacturer designs it to comply with certain rules. They're called etiquettes, which include constraints on how much power you can transmit at, what should happen if you hear someone else using the channel. All those kind of things are defined, but otherwise, as an end user, you don't need to get anything. It's also free in the sense that it's a shared part of the spectrum, so no one owns that part of the spectrum. Okay, and there are other ISM bands also. There is one in 5 gigahertz range. There are some higher range ones, and then also frequencies above a certain level are unregulated. So there are also sort of very high frequencies that go into it. But of interest to us are these two particular ones because the other thing is almost all countries have this. Okay, there's a slight difference between US and Europe. But 2.4 is universal. Every country has that. Okay, so it has emerged as kind of choice. If you had a choice between 2.4 gigahertz and 900 megahertz, what do you think are the trade-offs?
Size of the transmitter. As the frequency increases, the transmitter amplifier size can be smaller.
Not the amplifier, antenna size can be smaller. Antenna size. So this one will have smaller antenna. Why smaller antenna? Antenna size depends upon wavelength, right? This some fraction of the wavelength. So frequency increases, wavelength goes down, so antenna size goes up. Okay, so that's one advantage. What else? Which way? Power consumption, which way? What happens? So as frequency goes up, the ability to penetrate goes down. Or put differently, to reach the same distance, I need to spend more energy, right? So this is more. So if I for if, so for so this has better coverage, and so coverage higher, power lower. Okay. So and and there are also some free bands, ISM bands like stuff around 400 or so. Also, so you could use those. Also, the problem is the lower you go down, the bands are smaller. Here you have, I think, around 80 megahertz of free space. Here you have around 15 megahertz of free space. In the 5 gigahertz ISM band, you have around 700 megahertz of free space. So the reason simply is that the higher the frequency, you are able to have more room over there. So sort of product designers and all have to kind of strike balance. So that's what sort of goes on here.
Both these are unlicensed or?
They're both ISM. Yeah. Okay. So 15.4 has defined set of standards around these frequencies, and then Zigbee is an industrial consortium which is built on top of this, and you kind of see that slight differences in the frequency, 2.4 gigahertz worldwide, and what Zigbee and 15.4 under the hood provide is 250 kilobit per second, and the target is things which operate in months or a small number of years. Distances are short, and you cope with that short distance by having mesh networks. So Zigbee provides the mesh routing on top of it. And then, and this is a very important part, it's designed for very low wake-up time, 30 millisecond versus 3 second, and I might add this is for classical Bluetooth. Okay, and that is very important in you being one being able to duty cycle the system. You want to put to sleep, and if you wake up, if you were to spend another 3 seconds to discover your partner, it's a problem. Whereas this one is organized for very much more rapid wake-ups. And it has to do with both the protocol as well as the circuits. Okay, so this is a space where Zigbee and these things are operating in. Give you a sense of Texas Instruments, a company which makes ICs and all. They have a whole repertoire of radios for this. So it basically this kind of gives you a sense of what's happening. So there's a whole bunch of channels of 3 megahertz wide, and kind of the transmission takes place in one of the 16 channels that are allocated to Zigbee. And there are all sort of issues like you want to separate them out so that 2 nearby channels are not used in the same space, same location and stuff like that. So main thing is that what this Zigbee slash 15.4 defines are kind of 2 types of devices, and you don't need to read. This is kind of like simple stuff, simple devices. These are like your light switches or stuff like that. Okay, they may be battery powered. They're kind of like the leaf nodes of the network. And these guys are meant to be more elaborate. They can act as routers. So they are. They could be things like, let's say, a light bulb, because it has more energy plugged in. And in particular, they can act as coordinators. Coordinators meaning they can schedule things, they can act to manage kind of the whole network. So with that, what a typical Zigbee network might look like, a variety of things. So you might have this kind of a setting where there's a coordinator node and it's talking to potentially some other full function devices, complex devices, but also some very simple devices, kind of these light switches and all. You can have a mesh technology formed, and you can have a combination. So see, in case of this kind of stuff, they are all full function devices. But if you have a hybrid topology, then the red nodes, which are our simple nodes, they are talking to a coordinator node, but they themselves will never be in a position to be asked to route anything. So essentially, we have 2 kind of nodes now: those who are leaf nodes and those which can act as part of our infrastructure that we are constructing. And then, in terms of handling the traffic, what 15.4 does is, and this is coming from the 15.4 side, is that it divides time into these things called super frames, which is what you see out here. At the beginning, there is some special packet transmitted so that everyone gets to hear that there is a network out here, what's the time, and stuff like that. But for our purposes, the main thing of interest is that the rest of the time super frame is divided into two regions, two types of time intervals. So the bright green one is those which are reserved for guaranteed access. That is, we actually give nodes specific times. You can transmit at this time. So these are going to be things like sensors which need very precise timing access. Okay, and then this creamish color stuff is when we do a contention-based mechanism, a bit like 802.11. So during this time, you may try, the channel may be busy, you may have to back off, take your turn next time. So the green one is guaranteed, this one, and the creamish one is not. So it tries to support both kinds of traffic. So if you have acoustic traffic or sensor traffic and all, you might put it out there. On the other hand, if you have traffic which is delay tolerant and all, then you would put it in this green category. So that's how it's kind of designed. And then an additional mode it has in this thing is something called battery life extension mode. And kind of the idea in battery life extension mode is that you can actually go to sleep for long durations. And so I'll not go into the details of this one, but kind of the idea is that you can rendezvous at a particular point in time in future and then otherwise kind of go to sleep. You don't have to wake up in each one of these super frame periods. So as you can see, there are certain choices they made. Another choice, which I'm not going into out here, is that the modulation scheme they picked is designed so that the amplifier doesn't need to be linear and is designed so that the radio can be very rapid wake up. So exactly kind of the things that Wi-Fi goes in a different direction because it needs speed and all, this one goes in a different direction. Wi-Fi speeds, as you know, are, even the original Wi-Fi was in a few megabit per second. This is 250 kilobit per second. So, and nowadays, what's the current speed of Wi-Fi? Newer Wi-Fi standards. Anyone? What's the latest Wi-Fi standard? Don't Google. Come on. No. AC. Yeah. How much is the speed? Yeah, gigabit per second. Exactly. It's mind-boggling, right? I mean, we don't get that over wired even. So Wi-Fi has kind of clearly catering to a very different market. Zigbee, 250 kilobit per second, good for sensors, those kind of things. So it made all these design choices which are really optimized for power, short range, those kind of things. One of the challenges it faces is that it exists in the same band that a Wi-Fi AG operates, a standard kind of the old 2.4 gigahertz type Wi-Fi. So it has to coexist, and there's a lot of work which shows that there are serious issues of interference and all that occur between these. But that's what it is. There are people who have also shown that there are ways in which you can exploit this coexistence. There's some fool work happening in there. But broadly speaking, there is a possibility of interference if they're operating in the same place. Okay, and so that was Zigbee 15.4. I didn't go into Z-Wave because it's kind of operating in the same space. It's also a mesh network, very similarly architected. Kind of the underlying details are kind of less important. They're just different market segments. So ANT is the interesting one because that's the closest to what we are attempting to do in with Xavier, which is these are designed for very low power sensors, wearable sensors, coin cell based thing, very low data rate. So even though 250 kilobit per second sounded low, this is perhaps even lower. Years of battery life, and so the way ANT approached this thing is by doing this TDMA channels. So time division multiple access, so they divide time into slots and operate within that. So essentially, it corresponds to what was happening in this mode. Okay, so it corresponds to that, but designed specifically for uh, uh, small messages being sent relatively infrequently. So if you look at the payload, 8 byte, okay, very small messages, because the idea is that if I have a heart rate sensor or some other sensor, it's going to send a few bytes. That's all you're after. And within that, then it provides kind of a whole networking infrastructure. But this was entirely proprietary. Um, so this kind of offers some contrast of how these things uh, were positioned. But the main thing is that the AND devices were simple. You would see in other ways also, like what's the memory footprint? 2 kilobyte versus hundreds in the other case. Battery life, many years to a few months, and in case of classical Bluetooth, few days. Excuse me. Transmission rates. Sorry. And a whole bunch of other things. But the main part is really this was designed for this ultra low power kind of thing. The flip side was it was proprietary, and therefore companies hesitated to get into the space. And the other issue was you needed another radio, which would be to sort of work with. So, and while penetrated quite a bit in the health space, did find broader adoption. And so, what happened at some stage was that Bluetooth got BLE, and that overtook what ANT does. Not as well as what ANT does, but since it's part of the Bluetooth ecosystem, so it and built into your phone, so it ubiquity basically kind of helped things. So this shows you like uh, what why things like ANT or BLE are kind of needed. So in this case, what we're showing is for messages being sent at a certain duty cycle, what kind of advantages that you get. So you are seeing classical Bluetooth, you are seeing ZigBee, and you are seeing ANT. And again, bear in mind that you're unlikely to operate ZigBee and Bluetooth in these modes, but were you to do it, it kind of shows the difference. That as message period increases, that means I'm transmitting messages less frequently. The gain increases quite tremendously with these kind of things. So, for the so-called ultra low duty cycle, low regime, very low frequency, like let's say, for example, a sensor on your door, which will send a message only when an event happens. These kind of things are very low rate, and essentially ZigBee, Bluetooth, these kind of systems are just not designed for that regime, and was, and therefore kind of excels in that space. So I'm going to skip rest of the ANT. You don't need to know this, but again, it's a pretty rich set of products, but again, like I said, is kind of obsolete. Main point I want to go is the following: that over the past some years now, starting with, so I guess BLE first came out on, I think, iPhone 5, if I recall right, and soon after kind of penetrated kind of all the smartphones. It actually came out of it really has, in a way, nothing to do with Bluetooth itself, other than the fact that it's done by the same standard body in a way. It came out of an entirely separate heritage. Nokia had a project called WIP-Tree, and at some stage when ANT-like applications became quite important, then they kind of took that WIP-Tree, grafted it onto Bluetooth, and that's where it came. So transmit short bursts of data for years. That's kind of the goal. And approach really is we want to keep the radio asleep most of the time. And so you want to get radios into a stage where, firstly, they're rapid, they can be woken up rapidly, put to sleep rapidly, so that's very important. They should be optimized for very small message sizes. So that's another aspect which kind of becomes very important. And then all those other issues I mentioned, that the amplifier should not require high linearity because that ends up wasting energy. The radio should be designed should be such that it can be rapidly woken up. All those kind of issues, lessons learned, basically kind of got adopted, and that's where BLE kind of emerged. And what they did for BLE is, or BTLE is, that they actually made use of the advertisement messages that already existed in classical Bluetooth for purposes of doing that initial pairing. And I was looking at slide, and he kind of talked somewhat about that. But that's what happened out here. So let's do the following. Let's take a quick 3-4 minute break, and while I switch over the slides. Are all of you ready with your project ideas? You guys, you never met me.
No. Yeah.
So what's the project?
I'm not sure yet.
Not sure yet.
Like, I guess it depends on like the scope that you're looking for, because.
Well, until you talk with me, you wouldn't know that, right?
Oh yeah. Also, we were wondering like decide to take something more like homework assignments and whatnot. Like how much.
No. I think the homework assignments are just going to provide you the skills behind it, not give you project ideas. So I think you come and speak to me.
Okay.
Why don't you come to my office after today?
Okay.
Okay. You are. Which team are you part of?
I came to meet you the other day when you were in the traffic thing.
Oh, okay.
I was falling and not well, so I had to leave.
Okay.
But my teammate met me. We're
When-
coming again today.
Okay. Okay. So you're coming. Okay, cool. Yeah, I mean, I've been giving, when people who are coming, I'm giving them the ideas also, so that will
Okay.
tell you also. But also, I want to listen to what ideas you may have in terms of applications or. All of you have set up your Raspberry Pi? Huh?
Seems my voice, my laptop can't be made shareable.
Were you the Windows 10 comment? No. Okay.
But I don't even have a sharing tab, and I found that hosted networks are not supported. I'm not sure.
Okay. Come and meet me, and if not, I'll direct you to one of my students. Okay. It's Windows. Right.
Okay.
Okay.
Sorry, so what's the problem with not expanding the image?
Oh, so the thing is the following: when I shrink the image, it makes the file systems just the right size to host the content.
Right.
So there isn't a whole lot of free space there. So if you were to install anything further, then it is whatever that 5.6 gig file system it is. So so if unless I'm wrong about my how Etcher is working, but I think Etcher just creates a 5.6 gig partition, 5.6 gig file system, and the rest of the space is left unused on the card. Now, one of the things you could do is when you log on to Raspberry Pi, you can expand the partition. Okay, and so if you Google for expanding partition, it will show you the instructions. So that's one way of doing it. Is so if you're comfortable doing it, just go ahead and do that. Okay, but otherwise, it basically is leaving that unused. So there is some free space, but that's still there. But at some stage, you're going to run out of that, even though you have roughly 2+ gigs. Okay, so let's start. So some of this might be a recap of what Amr sort of covered, but hopefully not to the same level of detail that I would. So with this sort of history of sort of what happened on wireless in this embedded-ish kind of space, so BLE emerged out of the desire to have extremely low duty cycle, low data rate, very long lifetime kind of spectrum, as opposed to classical Bluetooth, which was kind of focused on streaming audio and these kind of things, and it suffered from these kind of issues like you had to pair, you had to, the devices took seconds to discover, and actually left unsaid also, but something I've said earlier previously, which is Apple never allowed classic Bluetooth without getting an expensive license from them. Okay, so while the phones were capable of classical Bluetooth, in particular serial profile and all, Apple's own products were using it, and there were third-party products, but those third-party products had to build a chip so that they can interwork with it, and that license to that chip was lots of money, to the extent that even as academics, because we often wanted to put sensors onto iPhone, we couldn't because Apple would only deal with companies. Android, on the other hand, had a flourishing ecosystem of sensors which were using essentially so-called serial profile. Essentially, your Bluetooth seemed like a serial port. Okay, that was very common. The problem was they were pretty power hungry. So while they existed, again, sort of quite a bit of a challenge. You can walk past the sensor and it will never even know you were there because the pairing process was this long. So I guess Apple kind of perhaps felt that it wasn't ready for this domain, so they never adopted it. Android allowed it, but so BLE was something that when first came out, as I said, on the iPhones, and no license needed if you wanted to make a BLE device. So it just caught on quite a bit. Okay, so what about it? So firstly, you will also hear the term BLE, Bluetooth Smart, means the same thing. There's some sort of trademark related issues out there, but main thing is that it was this is a subset of the classic Bluetooth, came out as part of Bluetooth 4.0. Bluetooth 5 came out a few months ago, so now we are in the next generation, but hardly any product has it. So okay, and I think most of the stuff I've already said. The modulation rate of BLE radio is 1 megabit per second. So this is the underlying thing at which the bits go over the channel. In practice, you are going to get some, let's say, 100 kilobit per second. Okay, lots of factors sort of come into play. Its focus is on very short range communication. In fact, many applications rely on really short range communication, so they operate the radios at very low power. So like for example, if you go to some stores and all where they deploy so-called BLE beacons. The idea out there is that when the customer is next to the product, only then it should kick in. So they want really small range, so they keep the power very low. So that's one part of it. It does allow though a fair bit of power variation, power setting, all the way from 0 dBm to 10 dBm in terms of power. Does everyone know what dBm means in power? Relative to 1 milliwatt. Okay, so that's what it is. So decibels relative to 1 milliwatt. Okay, so why is BLE interesting? Well, I think perhaps this was the biggest reason that now suddenly you had something which worked universally. Yeah. At this stage, pretty much there's good solid support for it all around. You have Linux stack, so that's why we are going to be able to use Raspberry Pi as well. So some terms and some of them could be potentially sort of confusing a little bit. So server is something which has data. Sensors have data, therefore sensors are servers in Bluetooth parlance. That sounds counterintuitive because oftentimes we think servers are big. That's not the case. Servers are what have data, and so that's the order. So they are our peripheral devices. And then clients are the ones who need the data, they are the central devices. Now, depending upon setting, a device could play both roles. So for example, Raspberry Pi could play either role or my phone could play either role. Like sometimes my phone may be peripheral, sometimes it may be the host side. Hexaware is only capable of being a peripheral. Okay, typically the sensors, tiny sensors, are designed to be on that side of things, on in the server or peripheral mode. Okay, another term. Yeah, by the way, these slides are all this set of slides. The black ones are from Apple. I forgot to acknowledge them out here. So what happens is, so now one of the ways Bluetooth attains, BTLE attains this thing of anyone can talk to it, immediate connectivity, not that wait for 3 seconds and all, is that it essentially is a connectionless system. And the idea is that the sensors can send data by piggybacking the data on advertisement packets that Bluetooth already had. Bluetooth had advertisement packets to be able to do the pairing, the discovery pairing. BTLE kind of uses them to also send the data. So on the advertisement packets, I think there are 31 bytes or some certain amount of payload, small amount of payload. So sensors can advertise themselves and they can advertise certain data along with it also. And it's the listener's job, your iPhone or Raspberry Pi or whatnot, that it will go into scanning mode. And when it is scanning for the advertisement packets of the right type, then it is going to listen to this. And this advertisement interval is kind of like your duty cycling period, right? So you can set the advertisement period to be low or pretty high. So you may have seen these kind of products like key fobs, which are BTLE key fobs, so that if you lose your key, you can discover them, or baggage tags. There are a lot of these applications which are emerging. And the advertisement interval is set relatively low there to be able to keep the power consumption low. If I keep the advertisement level there low, so battery improves, what takes a hit? Nothing tricky about that question. Latency with which you will discover something, right? And then there will be a longer delay to discovery. Okay, so that's kind of one of the basic operation that is happening. Now there are several different advertisement channels that exist. So that advertisement, an advertising device may advertise itself on all the 3 channels, and so 9, and the scanning device may scan in different things. So the idea out here is, why do you think you might want to advertise on multiple channels? Why do we have multiple advertising channels? If we are going to send them on all three anyway.
Maybe faster chances of finding it and fair enough for this.
Okay, fair enough. So one thing is faster chances. Sure. What else? Although that is less of an issue.
Dependability.
Huh?
High
Dependability.
redundancy for dependability.
Why? Yeah, you're kind of on the right track. So what hurts dependability?
Once collisions might happen on one channel or it might get lost.
Okay.
Isn't frequency hopping here?
Yeah. What else exists in 2.4 gigahertz band? What? Think of your home. Is there something which? Well, firstly, you have Wi-Fi and stuff like that, right? I mean, so it could be that this channel is getting crashed by Wi-Fi which is operated, not the other one. So that's one part. But can you think of something which operates in 2.4 gigahertz at your home?
The microwave?
Microwave oven, yeah. Why does microwave oven operate in 2.4 gigahertz? How does microwave work? Microwave oven, I mean.
Like high heats the food.
Huh?
During high heat the food.
Yeah.
It resonates, like it's the resonant frequency of the water.
Good. What's the resonant frequency of the water molecule?
Okay.
Exactly. So that's why it operates there. So resonant frequency of water molecule is there, and that's why it has to operate there. There was no choice. Okay. So moving on. So there are multiple frequencies. Okay. So now what happens is yeah.
Question. If like microwave and Bluetooth and Wi-Fi all contend for similar like gigahertz range, and there's like a group of people who decide what frequency range to give, how do they just make like Wi-Fi and Bluetooth take different frequency range from like?
Because you can't coordinate, right? I mean, think about these things are coming from different product lines, and also you're saying why did they not design them so that they're
So like yeah, like Wi-Fi operates on 3 gigahertz.
just imagine the coordination problem at the level of manufacturers and all that what exists. So the idea out here is, by the way, that's one thing. The other thing is actually the rules of operation of this ISN band require that you adapt to whatever the thing exists. Okay, so that's why multiple channels, hopping out of it, smart discovery of the channels, and also microwave doesn't operate all the time, right? I mean, so a lot of time the channel is free. So yeah, variety of reasons.
Microwaves are also good Faraday sheets.
Yeah, sure.
Like, doesn't it play a role?
Nope. I mean, you operate a microwave and you'll see the interference that you get. Yeah. Okay. So what's happening out here then is that the basic thing is we do advertisement. In that we contain some data, and these guys are scanning and receiving. Now it turns out that so in this mode, thus far, the sensor is advertising and anyone can hear it. There are multiple iPhones and Raspberry Pis and Android phones, they'll all hear it. Okay, as long as they're scanning, it's fine. It's one-way transfer of very limited amount of data. But there is an additional capability in BTLE which allows the central guy to now make a connection request. And once that connection request is made, then there is a one-to-one connection. So phone can, or the central guy can talk to one, whatever. A sensor can be connected to one phone only. Okay. A server can be connected to one client only. That's the way. So once that connection is established, then bidirectional data exchange can take place. So for example, let's take Hexaware. If Hexaware only has to send out temperature data, let's say, it can just piggyback on the advertisement. Nothing is needed. But if on the other hand, you want to blink the LED on Hexaware from your app running on your phone or Raspberry Pi, you have to establish the connection. There is no other way for getting the traffic in the thing. If you also need to do bulk transfer, like for example, Hexaware allows firmware to be sent over BTLE. This is not with mbed, but if you were to look at Hexaware's native firmware, which is there when you first got Hexaware, right? It actually has its own apps, and those apps can be pushed to it over BLE. So that's like a file transfer taking place. Again, you need the connection establishment capability. Okay, so then there are all sort of other things that one sort of plays into this thing, which is how long is the connection, just like we had advertisement period, how long is the connection for, all those kind of issues sort of come into play, terms associated with it. So topology wise then what is happening is that when we are in the advertisement mode, one sensor, multiple observers. So if there is a BLE beacon sitting out here, or your Hexaware transmitting some sensor data, then any Raspberry Pis nearby can hear it. Very important, Hexaware cannot be the observer. It doesn't have the capability, or at least I believe it doesn't. I have to verify that, but certainly can operate in this mode. Raspberry Pi can operate in both modes. Your iPhone and Android devices can do in both modes. Once you have the connection, then you are in this mode. Peripheral can talk to one central only. Okay, but then now you can do bidirectional and bulk transfer. So as you think about how to use Hexaware in your projects with the Raspberry Pi, bear in mind that sort of what we are playing with here. And by the way, as I had mentioned at the very beginning of the course, the reason we are using Raspberry Pi as in this role is so that everyone has the same thing. If you already know how to program an Android device or an iPhone device, you can use that as easily. And the Hexaware app that comes is that's what they are doing. Okay, so now going into a little bit more nuts and bolts. So over the air rate is 1 megabit per second. Yeah.
So how much power will the scanning mode take?
How, like not doing anything? Oh,
Not
scanning
doing-
mode.
Yeah, in the
Scanning mode is
context
pretty power hungry.
So if you choose to put your device in scanning mode, you're realizing that you're using up so much of power for that amount of time.
Yeah. And that's why, I mean, if you think about, you scan for long durations, whereas you advertise for very short durations, sporadically small packets. So one of the things I'll discuss in the next slide set is that in short range radios, transmitting packets can be cheaper than listening to packets. Okay, which is sort of counterintuitive, which is not true for Wi-Fi or cellular radios, but for short range radios. And the reason is, if you think about it, who has the harder task? The person who just has to encode, or the person who has to decode data from noisy, corrupted signals coming in? The latter is algorithmically more complicated, right? I'm getting a noisy bit stream back, and I have to recover a good bit stream out of it. So algorithmically, receivers are more expensive, and since we are operating in a low range, short range mode, my amplifier is not consuming my power. So by the time you hit Zigbee and Bluetooth, you are into the mode where receiver takes more power. And another comment I make is listening is no more cheaper than actively receiving. There's very little difference between the two. And therefore, if you're simply scanning, that's kind of like actively receiving, and receiving is more expensive. So that's kind of a long-winded answer to your question. It uses frequency hopping, something I already mentioned. So when we say channel, we really mean frequency hopping, okay? A particular hopping pattern, okay? And this is synchronized hopping. And the idea is that as we are hopping through a bunch of these frequency carriers, we may encounter once in a while some bad ones, but since we hop away from it, we are okay. Originally, frequency hopping was invented by, like I said, Heidi Lamar, the Hollywood actress, for security purposes. The idea is that if I want to transmit something to you, we two will have a shared secret as to what the hopping pattern is. Someone else who's trying to snoop doesn't. So even though once in a while they may see us at a particular frequency, they don't know where we went next. Okay, that's how it originally came, and there the hopping patterns are cryptographically based, very long, but the same idea also helps against interferers. If let's say my microwave oven in that home is the one which messes with channel number 20, well, we will be resident on channel 20 very little time. So kind of answer your question, which is why don't we design things? Well, this is why we designed this way, that if in one home microwave trashes channel 20, in another home it trashes channel 22, my system will still work. So there are three RF channels, as sort of we discussed previously also. So now Bluetooth originally was designed with this concept of profiles. Profiles are nothing but a set of rules kind of built on top of the basic Bluetooth. And one of those profiles was something called generic access profile. As the name implies, this is a profile which was meant for initial connection establishment and all. And as part of that, they had this whole concept of advertisement packets and all kind of built in. So makes your device visible to the outside world and determines. Okay, so that was the original role. This is what BTLE ended up kind of using. So we already saw it. It has peripheral devices, which are the more resource-constrained things, like our Hexaware, and it has central devices. This would be your laptop or tab phones, or in our case, Raspberry Pi. So there are two ways to send out payloads in this whole system. So one is the initial advertisement that you are sending out. You can include some data in that. And then there is also there is a second opportunity. This is still without establishing a connection, where a peripheral may send a response, an acknowledgement to your advertisement, and in return you are allowed to send a scan response. Okay, and that they are both payloads are 31 bytes. So essentially, the advertisement data, the initial one, is mandatory. It has to be always transmitted. Has to follow certain protocols and all. The scan response payload is an optional one, and devices have to request it. So the main idea is that you can essentially send 62 bytes. Okay, that's really what it kind of boils down to. If, by the way, if the scan central device kind of request it, okay. So 31 bytes is mandatory, the next 31 bytes is. So you can do a lot when it comes to kind of sensing type devices and all by exploiting both these capabilities. So this is what this figure is showing. Advertisement data coming in, once in a while you will see a scan response, and then there was a scan response request, and then there will be a scan response data in response to that, right? So and each one of these is 31 bytes. So 31 bytes. Yeah, so each one of these is 31 bytes. Rest of the stuff, what kind of advertisement intervals exist, milliseconds to seconds. They are settable in most of these practical devices. You will find longer the delay, the usual trade-off of latency versus energy that you are going to see. And then if a listening device is interested in the secondary payload, the scan response payload, then it is going to request the scan response and the peripheral response with additional data. Okay, so without creating any connections and all, that's the mode. You always advertise something from your peripheral, and in response to request, you send some additional data. Okay. So the piggybacking that is happening out here is that originally these advertisements were meant to help establish the connection. A device is saying, hey, I'm here, hey, I'm here. And what BTLE did is it basically says, we can also use the advertisement packets to also advertise data. And the beauty out here is that no connections are needed. So in the classical Bluetooth, all of this was used to then establish the connection and then exchange the data. We bypass the whole thing. So this became very good for connectionless sort of transmission of data. So one-way data, and in fact, the big sort of explosion in this thing was when Apple, using on top of BTLE, built something called iBeacon, which were basically these tags which just advertise some information. Okay, in particular, they advertise UUID. Anyone knows what UUID is? Hmm?
Guessing unique user ID.
Like the unique ID for your.
Universally unique identifier. So it's a long bit sufficient to encode every particle, subatomic particle that can exist in the universe and more. Okay, but so the main point is we can give everything a unique ID. Okay, so what iBeacons is, they basically send out this unique ID, and then the applications are designed to look for specific IDs. So, like for example, Macy's app on my phone will be on the lookout for the UUID that Macy's is using, and then whenever it sees that, it says, "Aha, I'm at a Macy's store," and then it can start pushing ads at you. That's kind of the concept. So it inserts a custom payload in the main advertisement packet because that payload allows for some manufacturer specific data field. Those are kind of the details, but kind of the high level concept is that some stuff sort of gets put out there so that your apps can then sort of make use of. Once once a connection is established, though, then a sensor is paired, has a connection with a particular central device, and at that point, during that time, no more advertisements are done. So, for example, a lot of these iBeacons that I described, they come with the ability that the manufacturer gives you an app so that you can establish a connection with the iBeacon and then configure it. Like, for example, you could configure its advertisement interval. You can configure its transmit power, those kind of things. Or in case of Hexaware, you could establish a connection to tell your software running on Hexaware that it should advertise the sensor data at a different rate. Or for example, it may say, I'm interested in temperature in centigrade versus Fahrenheit. You can imagine all sorts of things. Point is that once I have a connection, I can do something to that one device. And to do that, it uses another profile called CAT. And which I'll probably not get time to get to today. So yeah, I'm beyond time. So I'll pick this thread up later. But we'll also be on the lookout on Piazza. I'm going to send some additional material. There's no discussion section tomorrow. Tuesday, Amr will be there. Wednesday, I'm doing kind of makeup lecture / review thing. So send me questions. I'm also going to circulate things, but I'm basically going to be asking kind of questions which are really just to test your comprehension of the material. They're not going to be long problem solving kind of thing. But anyway, if you can come on the Wednesday session, I'll certainly, the way I record it, I will do that.
What time was the one on Wednesday?
It's 6 to 8, and I think the room given to us is